Welcome back to ECE 442-542. Must be the day after an exam. So I'll announce when our second exam is going to be. Not quite a month from now, so you actually have a spring break, I think, between now and the exam. It's going to seem like it's a long way off, but it will be here before we know it. I want you to get it on your calendar. So put that date on your calendar, the 13th of March, and it will cover homework number 3 and 4, or the topics that are addressed in those two homework sets. Today what I want to do is talk about the region of convergence, ROC, and it's really needed to find the inverse Z transform. When we were calculating the Z transforms, if we didn't have to go the other way, or if we didn't have to go back into the time domain, it might not have been as critical to know what is the region of convergence. But now if we want to go back and forth, it's very important to know what the region of convergence is. The region of convergence is really there to allow these sums to actually be bounded, to have a finite value. And we'll go through some general patterns. So after today you should have a feel for what these region of convergences might look like in general. There's really just 3 main patterns. And we'll go over those and why they might be what they are, and it's all based on the definition of the Z transform. Capital X of Z is given as this two-sided sum where the index on our sequence of values, X could be a signal or it could be associated with a system. If it's associated with a system, X is really the impulse response or the pulse response of our system. So you could have this Z transform of a system, or you could have the Z transform of a waveform. But I'm now showing you sort of a couple of the pieces on either side of the n equals 0, or the origin part of our Z transform expression. Here's something that I think people get tripped up on, so let me try to give you the big picture or the main patterns, but this statement about the region of convergence, and I'll just abbreviate that ROC. The region of convergence is determined independent of any stability considerations. What I'm meaning by that is it doesn't matter how X of n behaves with time. It could go unbounded, it could be bounded. That doesn't influence the region of convergence. The region of convergence is determined independent of how X of n is evolving or moves or fluctuates with time, or with n, I should say, with index n. However, a signal is bounded or a system is stable. Like I said, X could be a system or it could be a signal. So if it's a signal, is that signal bounded? Or if it's a system, is the system corresponding to a stable system? If that signal or system is stable or bounded, then the region of convergence associated with that signal or system needs to contain the unit circle. The unit circle will lie inside or on top of the region of convergence. And hopefully that will make sense when we finish up or near the end of today's class. One more fact that I think you need to put under your pillow this semester. That pillow is getting used a lot, isn't it? But poles, these x's on the z-plane, they never lie on the region of convergence. If you have a region of convergence, you better not have x's in that cross-hatched area or in that shaded area of your z-plane. The z-plane is going to contain the region of convergence, but that region of convergence cannot have poles lying on top of or in the region of convergence. So let's get started with different region of convergence patterns. I've now sketched ahead of time so that I could maybe draw a legible axis. It's still not very good, but you now have a real line and a imaginary axis in the z-plane, and I've sprinkled 5 poles down on that z-plane. And for pattern number 1, not sure what color I want the region of convergence to be. Which of these poles is furthest away from the origin? I'm wanting your input so that I can try to draw a circle. I'm going to try to draw a circle just at the edge of the one that's furthest away from the origin, and I'm going to guess that it's the one on the real axis. That's how I tried to draw it. So my circle is supposed to have a radius, and it doesn't, but it's supposed to be a radius, the length or the distance that that outside pole is away from the origin. Is that clear? That's supposed to be a true circle. And the region of convergence for pattern number 1 is beyond that dashed circle. That's the region of convergence pattern number 1. It's the entire z-plane with a circle cut out of it. And the circle, inside or interior to that circle, are all of the poles in the signal or associated with the signal or with the system. And here's how I will describe that. I will say that the region of convergence is unbounded with a central void. Unbounded in this case really just means that the region of convergence goes all the way off to infinity. The region of convergence goes all the way in every direction to infinity. It's the entire z-plane, this region of convergence, with a circle cut out of it. And that circle is centered about the origin in the z-plane. This unbounded region of convergence has nothing to do with whether x, little x of n, is bounded or unbounded. Is that clear? So I use bounded and unbounded in 2 different domains. The frequency domain and the time domain, or the sequence domain. Yes? So now the question was, I'm assuming something about little n, the sequence on my, but you're getting ahead of me. So I'll try to answer that question is, what does this mean, little n, it consists of with respect to x of n, where n is the argument on our signal. Here's how I will describe that region of convergence. Either 1a, or whoops, I was supposed to have this as 1b. So there's 2, what I'm assuming are equivalent descriptions of that region. The region of convergence lies beyond all poles. That's one way of describing that pattern number 1. Or all poles are interior to the region of convergence. Whichever way you feel more comfortable thinking of that region of convergence. This is pattern number 1. If this is now the z-transform of little x of n, can we say anything about particular x's in this infinite sum? Right now this infinite sum is summed from minus infinity all the way up to plus infinity. But we said in this particular pattern, z goes off to infinity. Z is marching off to infinity because it's unbounded. What does that say, or does that say anything about some of these terms? We want x of z to actually represent a bounded expression. Can capital X of z remain bounded with all of these terms present? If this pattern, if this region of convergence goes off to infinity? Is it maybe, I'm not sure if it's clear what I'm trying to say, but now let's assume, let's just put a point over here. That point belongs to the region of convergence, and this we are going to let go off to infinity. Z as a complex number can get big. It's going to go to infinity. What happens if we plug that right there? Or what if we plug it right here? Or what if we plug it anywhere there, because there we have z raised to higher and higher powers. And if capital X of z is bounded, what does that imply about little x of n? If we have infinity times a number, what's that result going to be? And then we're going to add it to infinity squared times another number, plus infinity cubed times another number. Does that give us a bounded result? No. I'm hoping you're starting to see that this x at time minus 1, x at time minus 2, these have to be 0. Those can't be in this series expansion. This pattern then, if z is marching off to infinity, is really saying that we can't have this, we can't have that, and we can't have any of these terms there associated with z raised to, basically, since z to the minus n and n is negative, it's really like z to a positive power when n is negative. What's that mean then in terms of the implication? What I'm trying to imply is that little x of n is causal. Or another way of saying that is x of n is equal to 0 for all n negative. We can't have any non-zero sequence values with the index n being negative for this region of convergence. Pictorially, if we now sketch this x of n, now it might look like, well, it could have something at 0, it might have some value at 1, it might have some value at 2, at 3, at 4, at 5, etc. But it can't have anything non-zero to the left of n equals 0. That's what corresponds to, or that's the implication of this first pattern. If you have this region of convergence pattern, you can immediately say, oh, I have a causal sequence, x of n. You don't know how it's behaving, but you know that it's only defined for n greater than or equal to 0. Little x is only defined for non-negative values of its index. Did that help answer your question? The question was, well, this region of convergence implies that little x of n has to be 0 for negative values of n. Or maybe that was the comment. Maybe it was a comment and not a question. Are we okay with taking that region of convergence picture, pattern, and implying something to capital X of z. If X of z is defined, it can't be blowing up, which forces all of those negative indexed x's to be 0. That's what happens, or that's the implication of pattern number 1. That was so fun. Let's look at pattern number 2. You didn't have to laugh quite so loud. You might have even picked up on that remotely if you're watching this. Now, I want to do just the opposite with this pattern, meaning now I want this pattern, I guess the last one was in black, so now I want to draw a circle. Oh man, you guys can get out. I'm afraid I'm really going to have a disaster. I'm giving you time to sketch your circle. That's what I'm doing. That looks kind of like a football, but it's supposed to be a circle. But now what I'm doing is I'm actually going to shade the interior. What is shaded, did I label the last one? This is the ROC out here that's shaded. Here is the region of convergence for pattern number 2. It's interior to all of the poles. All of the poles lie outside of that region of convergence. And that's what I'm trying to describe here in words. The region of convergence is a bounded disk. It's bounded by the pole that has the smallest radius from the origin. That's pattern number 2. I hope you can see a difference between pattern 1 and pattern 2. How will I describe this one? Hopefully it's believable in terms of the wording. Here, the A description says that the region of convergence lies inside all the poles. Or another way to say it is all poles are exterior to the region of convergence. Whichever one of those descriptions makes the most sense to you, that's what you should keep in mind with pattern number 2. What did we do with the last one? We looked at our definition and we tried to infer something meaningful about x, or when little x of n is defined for the appropriate region of convergence. In this case, can we find an extreme value? In the first pattern, we went really extreme. We went to infinity and said, oh, if infinity belongs to that region of convergence, let's plug in infinity for z and see what has to vanish. Well, let's look at the extreme point in this region of convergence. What's an extreme point here? The origin, 0. If we now look at this extreme point right there, and that belongs to this region of convergence, does that tell us anything about some of these terms in this series expansion? Now we have little x of 1 divided by z, little x of 2 divided by z squared, little x of 3 divided by z cubed. We can't divide by 0 and have a bounded capital X of z. The z transform won't exist if those positive indexed x's exist or are non-zero. These have to vanish in this for this pattern, because now we're substituting in z equals 0 to all of these, and that now eliminates or forces these terms to equal 0. What's the implication now? Now I'm going to say that little x of n, it's definitely not causal. Causal is associated with the non-negative values of the time sequences argument. This is the opposite, so this is non-causal. This one is acting before it's excited. So we'll call that non-causal. Or we could say that x of n must equal 0 for all n that are positive. That's the implication of pattern number 2. And if we sketched that, we would now say, oh, we have something at -1, we have something at -2, we have something at -3, something at -4, something at -5, but nothing for n positive. N positive has to be 0. That's the implication of having a region of convergence that's a disk, that's interior to all the poles. We have one more general pattern. How do we come up with a pattern that's not the two that we just had? And now here is my pole pattern. I could have zeros sprinkled around, but zeros, it doesn't matter. The zeros don't impact this region of convergence. Here, what I'm going to do is I'm going to say that here is a circle, and here is another circle. And my region of convergence now is this since it's meal time, it's not the right time, but we could call that a donut. So this is now a donut shape, or an annular shape. We have some poles that are inside the region of convergence, some poles that are outside. Do we have any poles on the region of convergence? No, that wasn't allowed from our fact. We can't have any poles that are in the region of convergence. That's in contrast to inside the region of convergence. Here we have poles inside and outside. This pattern number 3 is annular, or donut shaped, or bagel shaped, whatever you want to call it. But it now has an inner circle and an outer circle. And here are my attempts at describing that. The region of convergence is a donut, or annular, or some poles are interior to the region of convergence and some poles are exterior to the region of convergence. And now if we look at this expression and we need it to be bounded, what can we say about the time indices, x at n's that are negative and x that are indexed with non-negative values? Was infinity a part of this region of convergence? Does that region of convergence go off to infinity? So that means that maybe we could have non-causal terms. Did it include 0? Did this region of convergence include the origin? No. So now we could have causal terms. The implication of this pattern is that x of n, little x of n, is a two-sided sequence, or little x of n is non-zero for n non-negative and n negative. And if we wanted to sketch that, now we can just go crazy. We can have values on either side of n equals 0. And we have to have, if x of z exists for this kind of a sequence, then it's really a tale of two tales. I know, but I'm trying to keep you awake. I don't see the pillow, so that's a good start, right? But now we have a tail on the negative indexed x's, and we have a tail on the positive indexed x's, and both of those have to sum to a finite value. Those are the two tails. And it's a story about those two tails, or a tale of tales. So all of those that are missing, maybe I'll have that on exam 2. I'll say, what's the tale of two tales? They probably won't watch this video either, will they? You could then draw this picture, a two-sided sequence of time. That's what I'm meaning by a tale of two tales. That's pretty easy, right? 3 patterns. First pattern had z going off. It had a what? The entire z-plane except a circle cut out from the middle. And what was in that circle? All the poles had to be in that circle. Pattern 2 was a disk. We don't know the size of that disk, but that disk is inside all of the poles. All the poles are outside that disk. That disk could be of radius 1/2, it could be radius 100, but all the poles are outside of it. Likewise for the circle that we've cut out of the z-plane, its radius could be 50. It could be 1/4. We haven't said yet. And then that donut, if we're hungry, it could be as big as we want. But it's bounded, isn't it? It's bounded inside and outside, and we have poles inside it and poles outside it. Now that we've learned that, let's throw in some variation. If you're eating donuts, you want a little variation, right? Well, let's look at the first 2 patterns. Let's look at variation. Let's look at a modified pattern number 1. And you're going, how can we modify pattern 1? What was pattern 1? It was something like this. It was the entire z-plane. Here is our z-plane with a circle in the middle, and all of our poles were in here. So let's say that there's right on the boundary of the circle, and then we have poles there. The modification is we are not going to allow infinity to belong to our region of convergence. The region of convergence will be outside this circle, but now this region of convergence is bounded because it's not going off to infinity. That's what this wavy box is supposed to be indicating. Here, the modification is, what if the region of convergence doesn't contain infinity? Or what if the region of convergence doesn't allow us to approach infinity? So our z-plane is not going to include the boundary, z going off to infinity. Or we could say that now our region of convergence looks something like the following. Suppose that this distance right here was R1. That's where that pole was. Then we're saying that z, the magnitude, is less than infinity and let's say bigger than R1. That's the region of convergence for the variation on pattern number 1. Yes? How do we do what? How do we determine the boundary of the region of convergence? It's going to depend on our sequence. Right now we're sort of going the other way. We're saying here is a region of convergence. What does that imply to the sequence in the sequence of values little x of n? I want to say time. In this class it's mostly a time sequence, but in other cases it could be an image. It could be something else. It could be of position. So I don't really want to always say time, but in controls, little x of n is usually associated with some time element. Now, what we're doing here is we're sort of starting with the region of convergence and seeing what that implies about that sequence, little x of n. What we're trying to do, though, is once we've learned these connections between the region of convergence and the sequence, we'll be able to identify where these sequence values are non-zero when we invert or perform an inverse C transform. R1, it's clear where that boundary comes from, is it not? In this modified pattern, what is R sub 1? That's as big as the farthest pole from the origin. That's R sub 1. The curly lines really are enclosing all of the z-plane except infinity. So another way can I make this even more confusing, because you're going to want to get confused when I say bounded. But I'm using bounded in both the frequency domain and the time domain. Here I'm using it in the frequency domain, and I'm saying that the region of convergence remains bounded. It doesn't go off to infinity. When it went off to infinity, what did this time sequence look like? Or what did little x of n do? Or what was it behavior-wise? For pattern number 1, was it causal, non-causal, or two-sided? It was causal, wasn't it? Well, now actually when we remove infinity, we generalize this causal waveform and we say that the sequence is now right-sided. So if this is now our variation on pattern 1, let's say that little x of n is now right-sided. Not just causal. Let me draw a picture of what I mean. When it was causal, x1 of n looked like this. Now I'm making a small variation, and I'm saying, oh, x1 of n is right-sided. That means its non-zero behavior is to the right of where it begins. But now I'm actually allowing it to begin at some finite negative location. It can have some finite indexes back to, let's say, capital minus m. Or I'm now saying that x1 of n is equal to 0 for n less than minus m, where minus m itself is negative. Minus m might be minus 10. That's all I'm saying. Minus m might be minus 1. That gives us a right-sided sequence. Most of the sequence, well, all the sequences to the right of where it begins. That's what I'm referring to as a right-sided sequence. A causal sequence is right-sided. But a right-sided sequence is more general than a causal sequence. That's what I'm trying to communicate with modified or variation pattern number 1. That received such a warm reception, I'm going to modify another one. Let's look at modification number 2, or modified pattern 2. That's supposed to be a circle centered at the origin. And let's say that here is, whoops. See, I don't even need a pillow to sleep or to fall asleep. I can fall asleep and lecture. That's kind of scary. What was pattern 2? Where were the poles? They were outside of the region of convergence. And in the last modification, I eliminated an extreme location. What if I eliminate the extreme location here? What's the extreme location in region of convergence, or pattern number 2? The origin. So now let me cut this piece out, and everything else is allowed. The region of convergence is still this disk interior to all the poles, except now we've eliminated the origin from that pattern. Now we're saying, what if the region of convergence doesn't include z equals 0? Or we now have our region of convergence bounded away from 0 and let's say less than r sub 2, where this distance radius-wise is r sub 2. What kind of a sequence, little x of n, would you guess exists now? Well, we used right last time. Maybe it's left this time. It's a left-sided sequence, and it's a generalization of a non-causal waveform. In this case, in modified pattern 2, let's call it little x sub 2 of n, is left-sided. not just, can I change up the wording and say anti-causal instead of non-causal? Same thing. You'll still get the full credit if you say anti-causal or non-causal. Picture-wise, in the time domain, here's n, here's x sub 2 of n. If it was non-causal or anti-causal before, it was something over here for -1, -2, -3, etc. And now we're allowing for something to go all the way up in the positively indexed location to capital N, where here n is positive and x sub 2 of n is equal to 0 when little n is, let's say, greater than capital N. What have we talked about so far? What kind of behavior are these little x of n's? Are they an animal with a... You can't see my animation if you're playing along at home, but you can stand up and wiggle something behind your backside to pretend that it's a tail. All of these had a tail. All these waveforms had tails. Yes? For pattern 1, where was the tail? Or pattern 1 corresponded to causal, non-causal, two-sided. Causal. Pattern 2, non-causal. It had a tail, didn't it? What about the donut region of convergence? It had two tails. Strange animal, but it had two tails. What if we don't have a tail? What if our sequence is finite in duration? Then what happens? Well, let's talk about it. What's the region of convergence look like there? All of these patterns, these general patterns, had tails in the sequence x of n. What if, let's say, x sub 3 of n has finite duration? Or finite interval of support. The little n, where it's defined, is finite in length. I don't know if this is going to be confusing or not. Can I say that x sub 3 of n is not equal to 0, let's say, between little minus capital M and capital N? It could be 0 in there, but it's definitely not going to be non-zero outside of those capital minus M and capital N. Or you could say x sub 3 of n is 0 for n less than minus m, or it's 0 for n greater than n, whichever way you like. What if that is our sequence, x sub 3 of n, and we want to find its region of convergence? What's that region of convergence? Where does it get its name? Region of convergence. It's the region in the z-plane, values of z, that allow this summation in our z-transform to converge or to be bounded. That's the region of convergence. If we have a finite number of terms in this sum that's forming our Z transform, what would you maybe anticipate the region of convergence consisting of? Then, our region of convergence can include, how do I finish this tail? But x sub 3 doesn't have a tail, does it? I'm using tail different ways. What can we say about the z-plane? What parts of the z-plane are possessed by our region of convergence, or are a part of our region of convergence? The region of convergence can include all of the complex plane except A, the region of convergence doesn't go off to infinity, meaning it doesn't include infinity, if this sequence is what? When did we have problems summing things up when Z went off to infinity? So we had problems there when? When we went off to infinity, we had causal behavior, right? When Z went off to infinity. So now, if it doesn't go off to infinity, we have something else happening, right? So if it doesn't go off to infinity, then we could allow what to happen? When it went off to infinity, what were we saying? We couldn't have any negative index terms, right, when it went off to infinity. Now if it doesn't go off to infinity, we can have non-zero x's for negative n's. Is that okay? I'm not sure I'm going to like the way I write this, but I'm now going to say if we don't go off to infinity, then x sub 3 of n is not equal to 0 for n less than 0. We can have non-zero x sub 3's for negative n's if we don't include infinity in our region of convergence. What about the other extreme case? What if the region of convergence doesn't include Z equals 0? When Z was equal to 0, we had problems when we divided by Z, or on our causal behavior of the sequence for indexes on x of n that were positive. So if we exclude 0, we can actually have non-zero values for x of n when n is positive. So let me see if I can write that down. So now the region of convergence, if it doesn't include z equals 0, if x sub 3 of n is not equal to 0 for positive indices. Let's look at some particular examples to see if we can clean this up or make it a little bit clearer. Examples. Suppose for the first one we say x sub 4 of n is made up of 5 delta of n plus 6 delta of n minus 1 plus 7 delta of n minus 2. I'm getting very creative with the magnitudes on those delta functions. Kronecker deltas. They're equal to 1 when its argument is equal to 0. What does this look like in terms of a plot of our sequence? If this is n, what's the picture of x sub 4 of n look like? Right at n equals 0, x sub 4 of 0 equals 5. So now we go up to 5, and we have a value. That's when n is equal to 0. When n is equal to, or when the second term in that sum is non-zero, is when n minus 1 is equal to 0, or when n is equal to 1. When n is equal to 1, we're up at 6. And at n equal to 2, we're now at 7. That's the sequence. X sub 4 of n looks like that. What's its z transform? If you were looking for partial credit on the exam, you would write that down, right? But x sub 4 of n doesn't have that many non-zero values. We have when n is equal to 1, when n is equal to 0, we have 5. And that's weighted by z to the power 0, or 1. Then we have when n is equal to 1, we have 6 z to the minus 1 plus 7 z to the minus 2. Or our z transform is now 5 plus 6 over z plus 7 over z squared. And what's the region of convergence? For these finite sequences, sequences without tails, it's the entire complex z-plane except maybe for some extreme locations. Is this still bounded? Is x sub 4 of z still bounded if z goes off to infinity? Is it well behaved? Is x sub 4 of z still well behaved if z goes off to infinity? Yes. Is it well behaved when z equals 0? We can't divide by 0 and have anything nice happen, can we? So the region of convergence here is the complex plane, the z-plane, minus the origin. It's the entire z-plane except z equal to 0. That's what I'm trying to say by c minus 0. That's the region of convergence for that finite sequence. What about another one? Suppose now I give you the following. Suppose x sub 5 of n is equal to 4 delta of n plus 1 minus 7 delta of n plus 2 minus delta of n plus 3. What values of n is this non-zero? It's when the arguments on that delta function are, or the values of n that cause the arguments of those delta functions to vanish. In the first term, we set n plus 1 equal to 0. We have something non-zero at minus 1. And that something is of value 4. When we set the second term's argument equal to 0, n plus 2 equals 0 says, oh, n is equal to minus 2. Now we're down at minus 7. And at minus 3, we're minus 1. And if we wanted the z transform of little x sub 5, what does it look like? It's 4 times some z, some power of z to the minus 1. And what is n? Corresponding to 4. Wasn't it that case when n was equal to minus 1? So that we now could say, oh, that's minus a minus 1. That's now 4z. What about minus 7? Z squared minus z cubed. What's the region of convergence for sequence 5? For these finite sequences, sequences without tails, we know it's the entire z-plane except maybe some extremes. Is this z-transform well behaved at the two extremes? If I let z equal 0, is this okay? That looks all right. What if I let z go to infinity? No, this isn't bounded anymore, is it? If z goes off to infinity. So now we have to say that the region of convergence for this sequence has to be the z-plane except z cannot go off to infinity. So the magnitude of z is less than infinity, or region of convergence 5 doesn't include infinity. Or region of convergence 5 remains bounded. I know you're having as much fun as I am. Where we've looked at one extreme not being included and a second extreme, what if we combine them? What does that imply to this finite sequence? Suppose that x sub 6 of n is now 2 delta of n plus 1 minus 4 delta of n minus 1. Now we have a sequence which we're calling x sub 6 of n, that has a non-zero value at minus 1 and another non-zero value at plus 1, where the non-zero value at minus 1 is 2 and the non-zero value at 1 is minus 4. And what's the z transform of x sub 6? Don't you hope I give you this to find the z transform of on exam number 2? So I have 2z for the first piece, and then I have minus 4 scaled by z to the minus 1 to what power? Minus 1 plus 1. What's the region of convergence for this sequence? Is it bounded? Can we let z go off to infinity and still have a bounded x sub, capital X sub 6? No, so we have to bound it. What about, can it include 0? No, because we're dividing by z, so now z, that's the kind of donut I want, isn't it? I could be chewing on that one for a long time. If you define your annular region to have a 0 inner radius and a very large outer radius. So here, the region of convergence for sequence 6 doesn't include z equals 0 and doesn't include z going off to infinity. And you're probably saying, so what? Why are we spending so much time doing that? Why are we so interested in this region of convergence? And the bottom line is it allows us to figure out what x of n looks like as a function of n. Let's get started on looking in that. Suppose, let's examine two different cases. Case 1. Suppose that here x1 of n is equal to 1/2 to the n for n less than 0. Just to give us an idea what we're playing with, what does this look like? Little x of minus 1, what's that look like as a value? It's 2. It's 1/2 to the minus 1, or 2. What about x of minus 2? 4. X of minus 3. You get the picture. Or if you wanted to draw the picture, which I wouldn't discourage, you now have 2, 4, and 8 for x sub 1 of n. And it just keeps going. What's the z transform of that look like? Or if I really wanted to get you nervous, I might say it's that, where U is a unit step. U is just a switch. And when is U going to actually turn on X in that argument for this Z transform? When is U of minus n minus 1 going to have a value of 1? For what values of n? If you plug in n equal to 0, you have U of minus 1. What's U of minus 1 equal to? 0. What if we plug in n equal to minus 1? U of minus a minus 1, minus 1. U of 1 minus 1. U of 0 is 1. So it's on. N equal to minus 2. You don't like my thinking? It's late. It's late. So this is turning that on for negative values of n. We can now say that this is going to be this summation from n equal minus infinity to minus 1 of 1/2 to the n z to the minus n. Or we could say, well, this is n from minus infinity to minus 1 of 2 to the minus 1 to the n z to the minus n. Or this is now 2 to the minus n, so that we could say that this is now this sum from minus infinity to minus 1 of 2z to the minus n. And that may be confusing, so let's clean it up. Suppose we now let L equal minus n. Since I like to play with positive powers. If L is now minus n, and n was going from minus infinity to minus 1, capital X sub 1 of z is now going to be this sum from L equal 1 to infinity of 2z to the L. And for what value, or what it, so this is now, if you, I hope you can see that this is a geometric series. And what's our common ratio? What's the term that's common to all of these terms in our series? 2z. 2z is the common ratio. Or if we didn't like that 2z, we could always say, well, this is like in calculus when we put in a variable, a dummy variable, or we redefine things. We said, oh, let's not have that. Let's just call it w. But when is this going to be well behaved, this sum? Now that we have something raised to higher and higher powers, positive powers, 2z, what can we say about its magnitude? Can we say anything about the magnitude of that relative to having this particular series bounded? Two z has to have a magnitude less than 1. Or the magnitude of z is less than 1/2. This is our region of convergence. And which particular region of convergence is it? Z is now interior to 1/2. This is the disk. This is pattern 2, and that's consistent because we had a non-causal sequence. We had an anti-causal sequence, so this is seeming to be consistent. Now we have capital X1 of z is w plus w squared plus w cubed, etc. We didn't have L equal to 0, but now we could say, oh, this is w inverse times x sub 1 of z is going to be 1 plus w squared plus w cubed, and the tails are going to be the same. And we can match up these terms on the right-hand sides. Meaning, if I now say, oh, I have 1 minus the inverse of w, or if I compare those two sequences, or if I subtract the bottom one from the top one, I end up with the following. The quantity 1 minus w inverse times capital X sub 1 of z is equal to minus 1. That now allows me to conclude that capital X sub 1 of z is minus 1 over 1 minus w inverse, or if I multiply by 1, which is w over w, I then have minus w over w minus 1. But we didn't start with w. We wanted a z. This is supposed to be capital X sub 1 of z. Capital X sub 1 of z, we replaced w with what we defined it to be, which was 2z. And that looks a little odd, so factor a 2 out of the numerator and the denominator, and we have minus z over z minus 1/2. And what was our region of convergence? Z less than 1/2. Well, let's see if we can learn anything from what we've just done. What's the pole zero pattern? Here's our z-plane. Where do we have any finite zeros? We have a finite zero at the origin. What about poles? We have a pole at 1/2. Where's our region of convergence? So here's 1/2. Our region of convergence is all of these values. Doesn't matter where the 0 is. The poles are what can't live on the region of convergence. Here's our region of convergence. Where's the unit circle relative to this disk? Unit circle is just where it's supposed to be, right? This is now our unit circle. Does the unit circle live on top of or in the region of convergence? Is it contained in the region of convergence? What was our time sequence, x of n? What did it look like as a time sequence? We started at 2, then we went back in time, we went to 4, then to 8. What's it doing as a sequence of on index n? It's blowing up, isn't it? It's going unbounded. And what do we know about the region of convergence and the unit circle relationship? The unit circle is not in our region of convergence. So that basically says that we have an unbounded sequence. Here are the observations I want to make. Relative to this example. 1, the time domain response, that was little x sub 1 of n, is unbounded. There I'm using unbounded to denote exponential growth in our time sequence. The unit circle doesn't lie on top of the region of convergence. So this is unstable. And here's the connection that we need to make. That if our unit circle is not in the region of convergence, then our sequence is unbounded. And I'll add another observation maybe after we stop, but that's one that I want you to sort of drive home. We have 3 patterns, some modifications to those patterns, 2 of those patterns, and now we've maybe seen a connection between region of convergence and the unit circle. We'll pick up with those observations next time.